Something changed in the data coming back from the most distant machine in human history. Not dramatically, not with a burst of static or sudden silence, just a shift, a reading from instruments 16 billion miles away that did not match what any of the models had predicted. Scientists at the Jet Propulsion Laboratory in Pasadena looked at the numbers and said the same thing they have been saying for years about this spacecraft. We were not expecting that. Online, that moment became something else entirely. Channels flooded with versions of the same story. Voyager 1 had turned around. It had looked back at us. What it saw had stopped the world. What it discovered could not be explained. The implication always the same, always just beneath the surface. Something out there turned it. Something out there made it look. Something we were not prepared for waited beyond the edge of our solar system, and Voyager 1 had found it. Here's the precise physical truth. Voyager 1 has not turned around. It cannot turn around. A spacecraft moving at 38,000 miles per hour, propelled by the gravitational assists of Jupiter and Saturn, accumulated in 1979 and 1980, with no engine capable of reversing its trajectory, does not turn around. The laws of orbital mechanics do not permit it. What the viral videos described never happened, and the blogs that wrote it, tracing back to a single low-credibility source that has fabricated Voyager stories repeatedly, did not source it to a single NASA document, JPL engineer, or peer-reviewed paper, because no such document exists. But here is what does exist. Here is what Voyager 1 actually found at the edge of our solar system. Data returned by real instruments, published in real papers, documented by real scientists. And the honest truth is this. What it actually found is harder to explain than anything the viral videos invented, because nobody predicted it. Nobody's model anticipated it, and it rewrote what physicists thought they understood about the boundary between our solar system and the rest of the galaxy. To understand the discovery, you first need to understand the place Voyager 1 reached, because most people, when they think of the edge of the solar system, imagine something like a shoreline, a clear line. Inside, our sun's light, our planets, familiar space. Outside, the void between stars, cold and empty and dark. The reality, as Voyager 1 discovered by being the first human-made object to physically cross into it, is nothing like that. Nothing at all. The sun does not simply illuminate and warm the planets and stop. It breathes. Constantly in every direction, the sun exhales a stream of charged particles, electrons, protons, alpha particles, traveling outward at speeds of 250 to 750 kilometers per second. This is the solar wind. It does not stop at Pluto. It does not stop at the Kuiper Belt. It keeps expanding outward into space, pushing against the material between the stars until it finally slows, compresses, and stalls. At a boundary called the heliopause, the official edge of the sun's domain, the point where the pressure of the solar wind equals the pressure of the interstellar medium pushing back against it from outside. Every model of the heliosphere predicted roughly the same thing about the heliopause. It would be a relatively clean boundary. On one side, the sun's magnetic field, the solar wind, the familiar environment of our own star's creation. On the other side, the interstellar medium, cold, sparse, threaded with the ancient magnetic fields of the galaxy, quiet. The transition between them might be turbulent, but it would be brief. Cross the heliopause and you were in interstellar space. Simple, clean, understood. Voyager 1 crossed the heliopause in August 2012 at a distance of approximately 121 astronomical units from the Sun, 121 times the distance between Earth and the Sun, roughly 11 billion miles. It became the first human-made object in history to enter interstellar space, and what it found on the other side of that boundary was not what the models said would be there. The first thing that was wrong was the temperature. Every model predicted that the plasma, the thin ionized gas, at the heliopause would be at a certain temperature. The solar wind cools as it expands outward. By the time it reaches the heliopause, the model said, it should be relatively cold. The interstellar medium beyond the heliopause is ancient, diffuse, and should be cold as well. There was no physical mechanism in any of the standard models that predicted anything dramatic happening to particle temperatures at the crossing. What Voyager 1 measured was a temperature between 30,000 and 50,000 Kelvin in the boundary region, not in the solar wind far from the sun, where temperatures can reach into the millions of Kelvin, not in the corona of the sun itself. At the heliopause, the outer boundary, the edge, the place where everything should be quieting down, Voyager 1's instruments recorded plasma temperatures tens of thousands of degrees higher than any model had anticipated. Researchers who processed the data described the boundary region as a wall of fire. Not fire in any combustive sense. There is no oxygen in interstellar space, nothing to burn, but a zone of extraordinarily energized, superheated plasma, created by a physical process that the models had not predicted and that scientists spent years working to understand. The explanation, when it emerged from the data, came down to a phenomenon called magnetic reconnection. The sun's magnetic field lines, carried outward by the solar wind, do not simply stop at the heliopause and wait. They encounter the interstellar magnetic field pressing inward, and where the two fields meet at opposing angles, they snap, they reconnect, like two elastic bands suddenly released from tension, and in that reconnection, kinetic energy is converted directly into heat and particle acceleration. The tangled, stretched magnetic lines of the solar wind, meeting the ordered lines of the galactic field, release energy in a continuous, turbulent process that fills the boundary region with plasma far hotter than anything on either side of it. As space physicist Dr. Amy Chen explained in a 2024 lecture at JPL, the magnetic reconnection process at the heliopause transforms kinetic energy into particle acceleration and heat, which explains the unexpectedly high temperatures Voyager 1 detected. This process is not exotic or supernatural. Magnetic reconnection happens throughout the universe, in solar flares, in the magnetospheres of planets and distant astrophysical jets. What was unexpected was its scale and intensity at the heliopause, and the degree to which the standard models had failed to account for it. The second thing that was wrong was the magnetic field itself. Before Voyager 1 crossed the heliopause, the models were clear about what would happen to the magnetic field. Inside the heliosphere, the sun's magnetic field dominates, carried outward by the solar wind, spiraling into the familiar Parker spiral pattern first described mathematically by physicist Eugene Parker in 1958. Outside the heliopause, the interstellar magnetic field takes over, a completely different field, aligned with the broader galactic magnetic environment, pointing in a direction that theory predicted would be sharply different from the sun's field. The heliopause, in other words, was supposed to be a magnetic boundary as well as a plasma boundary. Cross it, and the field direction would change. It did not change. When Voyager 1 crossed into interstellar space and its magnetometer measured the field on the other side, the direction of the interstellar magnetic field was nearly parallel to the direction of the solar magnetic field just inside the boundary. Not perpendicular, not sharply redirected, aligned, parallel, as if the two fields, the suns and the galaxies, were running in the same direction on either side of a boundary that was supposed to separate them. NASA confirmed this finding when Voyager 2 crossed the heliopause in November 2018 at approximately 119 astronomical units, slightly closer to the Sun than where Voyager 1 had crossed, reflecting the fact that the heliopause is not a perfect sphere, but shifts and breathes with the 11-year cycle of solar activity. Voyager 2's magnetometer measured the interstellar field on the other side of the boundary. It, too, was parallel to the solar field. NASA's official statement on this finding acknowledged it directly. The magnetic field in the region just beyond the heliopause is parallel to the magnetic field inside the heliosphere. Two independent crossings, 6 years apart, at different locations, the same result both times. Whatever the models had assumed about the relationship between the sun's magnetic influence and the broader galactic field was wrong. The two are not independent. They are in some way not yet fully understood, aligned, as if the sun's bubble and the interstellar space around it are connected by the very field lines the models said should separate them. The third discovery is the one that most researchers find hardest to categorize. In 2023, long after the chip crisis that had silenced Voyager 1 for 5 months and the engineering miracle that brought it back, the spacecraft's plasma wave subsystem, one of its two remaining active science instruments, picked up something that had not been heard before from interstellar space, a faint, continuous, low-frequency oscillation in the plasma of the interstellar medium. Persistent, consistent. Present across weeks and months of data collection. The team that analyzed this signal, led by Stella Koch-Ocker at Cornell University, published their findings in the journal Nature Astronomy. They described what Voyager 1 had detected as a faint, persistent hum of plasma waves in interstellar space, an emission in the frequency range of 3 kHz, present continuously in the data rather than appearing in bursts or events as previous plasma wave detections had. The researchers proposed that this hum represented a previously undetected mode of oscillation in the interstellar plasma, a kind of background vibration in the medium between stars, driven by the thermal motion of electrons in the plasma, maintaining a continuous wave emission even in the absence of strong solar events to excite it. Ocker described the finding as revealing that the interstellar medium is more continuously active, more persistently oscillating than anyone had anticipated. Previous detections of plasma waves in interstellar space by Voyager 1 had occurred in response to specific events. Bursts of particles ejected from the sun, traveling outward and eventually disturbing the interstellar plasma when they arrived. Those were event-driven, discrete, comprehensible within existing models. This hum was none of those things. It was continuous. It was quiet. It was everywhere in the data, like a note that the interstellar medium was simply holding without being struck. The researchers were careful, in the way that rigorous scientists always are, to specify what this discovery is and is not. It is not a signal from an intelligence. It is not a transmission. It is not communication. It is a physical phenomenon. The thermal oscillation of an ionized plasma medium, a natural consequence of electron behavior at the temperatures and densities present in interstellar space. But it is also something that no instrument had ever detected before Voyager 1 found itself deep enough in interstellar space to hear it. And the fact that it is continuous, that it appears to be a permanent feature of the environment Voyager 1 is moving through, means that interstellar space is not the silent, featureless void between the stars that the models had treated it as. It hums, quietly, continuously, at a frequency human ears could never hear, but that a 48-year-old spacecraft built from 1970s components is still sensitive enough to detect. There is a fourth story from Voyager 1 that deserves to be told, because it is the kind of story that human engineering rarely produces and that will not be repeated. It happened not in interstellar space, but in the minds and hands of the people responsible for keeping this spacecraft alive. And it is, in its own way, as extraordinary as anything the spacecraft has found. Between May 2025 and February 2026, Deep Space Station 43 in Canberra, Australia, the only antenna on Earth capable of sending commands to Voyager 1, was taken offline for major upgrades. Not completely offline. There were limited operational windows in August and December 2025 when commands could be transmitted. But for most of 9 months, the engineers responsible for Voyager 1 were working with a spacecraft they could instruct only occasionally across a distance of 16 billion miles through a communication channel that was available for only brief windows in a 9-month period. During one of those windows, they did something that should not have been possible. Voyager 1's primary roll thrusters, the small rocket nozzles that control the spacecraft's orientation and keep its antenna pointed precisely at Earth, had been experiencing problems with clogged hydrazine lines. Backup roll thrusters existed on the spacecraft, but they had been declared dead in 2004. 21 years of disuse in the temperature extremes of deep space had been assumed to have made them permanently inoperable. No one had tried to fire them since 2004. There was no particular reason to believe they would respond. The engineers tried anyway. Slowly and carefully, they designed a procedure to warm the backup thrusters, raising their temperature gradually through the spacecraft's heater system, attempting to clear the clogs in the fuel lines through thermal expansion, preparing the system as carefully as they could from 16 billion miles away before attempting a firing. And then, through one of the narrow communication windows available during the Canberra outage, they sent the command. The thrusters fired. Thrusters declared dead in 2004, unused for 21 years, responded to a command from Earth and fired correctly. Voyager 1's attitude control was restored. Its antenna remained pointed at Earth. The data kept coming. Suzanne Dodd, Voyager's project manager at JPL, stated in an interview that everything on board Voyager 1 is now single string, meaning there is no backup for any remaining system. Every component that is still working is the last of its kind on the spacecraft. There is no redundancy left. And yet it continues. Its 2 remaining science instruments still active, its antenna still locked onto the small blue planet that sent it out 48 years ago, still sending back data from a place no human-made instrument has ever been before. When Voyager 1 crossed the heliopause in 2012 and entered interstellar space, a researcher at the University of Maryland named Mark Swistak described the moment by saying that Voyager had gone from a beach on one side of the ocean to a beach on the other side, and found that the beach on the other side was completely different from what anyone had expected. The sand was different. The temperature was different. The magnetic field was different. The sound was different. Everything that the models had predicted about what interstellar space would be like, based on observations made from inside the solar system, turned out to need revision the moment an actual instrument arrived there and measured it directly. This is what exploration does. It does not confirm what we think we know. It tells us what is actually there, which is almost always stranger, more complex, and more interesting than the models predicted. The models of the heliopause predicted a clean boundary and cold plasma on the other side. What Voyager 1 found was a wall of superheated fire and magnetic fields aligned in ways that rewrote the textbooks. The models of interstellar space predicted silence between the stars. What Voyager 1 found was a continuous hum, persistent and quiet, in the plasma that fills the space between suns. Nobody built a viral video around the real version of these discoveries. They did not have the simple dramatic narrative of a spacecraft turning around and seeing something that stopped the world. They required context, explanation, and the patience to sit with findings that are genuinely uncertain, genuinely debated, and genuinely consequential. But that is what science actually is. Not a headline, not a turned-around spacecraft, a temperature reading that didn't match the model, a magnetic field pointing the wrong way, a sound that wasn't supposed to be there, and a team of engineers working through a 9-month communication blackout, reviving thrusters that had been dead for 21 years to keep an almost 50-year-old spacecraft talking. The discovery we can't explain is not what the viral videos claimed. It is this. A machine built in 1977, running on less power than a refrigerator light bulb, traveling through the space between stars at 38,000 miles per hour, is still there. Still measuring, still finding things. Still, against every reasonable engineering expectation, alive, and still showing us that the universe, at every scale and every boundary we dare to cross, is stranger than we imagined,